lecture on, well, you know what it's about.
Okay, hello. I'm impressed that so many of you came back. Thank you. So since this morning was so long ago, I have a slide reminding you a little bit about what happened. Yes. So the statement that we were thinking about was that certain quantum field theories in d space-time dimensions are the same, and that's what this wiggly arrow means, as certain theories of gravity in space-times which have one more dimension, so in d+1 space-time dimensions, with a certain time-like asymptotic boundaries, at which we should specify boundary conditions, one of which is that there's a time-like asymptotic boundary. So it's conveniently self-consistent. And we focused on an important special case of this for simplicity, because with extra symmetries, there are fewer things that can go wrong, and which is the case where that space-time is asymptotically de Sitter space. So it's a space-time with constant negative curvature, in which case that specification means that this field theory has a conformal symmetry. In particular, it has scale invariance. And the reason I know that is that this de Sitter space-time has isometries. It's a group of isometries are exactly the conformal symmetry of a relativistic field theory in d space-time dimensions. And I tried to convince you that this cartoon of de Sitter space as a bunch of copies of Minkowski space of size, a size which varies in a particular way in this extra dimension, is a different rendering of this same cartoon that I drew of a normalization group evolution. And so in particular, this extra dimension should be interpreted as the resolution scale with which we're probing the theory in question. And the fields living in this de Sitter space, such as the metric tensor field, or whatever other fields we might wish to include to construct some sort of consistent gravity theory that we like, correspond to the running couplings of the field theory. So the coefficients of terms in the Hamiltonian that evolve as we move in this direction. In the particular special case here of a conformal theory, they don't evolve, or rather they evolve in a way which is completely determined by scale invariance. But more generally, we could imagine other solutions where we perturb away from conformal invariance, in which case we would get some picture of the RG flow as a solution of some dynamical equations arising from a field theory in this background. And then to make this business quantitative, I mean, it's very nice to have pictures. It's also useful to have equations. The way that we compute the partition function of the field theory in the presence of some sources for a list of operators of our choice, in the limit where this gravity theory is a classical theory of gravity, is by extremizing to the best of our abilities the gravity theory path integral, which means solving the equations of motion of that gravity theory, subject to certain boundary conditions, which encode the information about the sources, and then evaluating the action of the gravity theory on that solution, and exponentiating it and multiplying by this factor which I called capital red n squared. So I want to explain why I called Newton's constant, or rather the thing that determines the number of degrees of freedom at each point in the field theory, which we figured out is related to Newton's constant, the parameter whose largeness ensures the classicalness of the gravity theory. So I called it this n squared because the best example that we know of a way to construct field theories which have these properties, a sort of a way to ensure at least some of these requirements to have a gravity dual, is by taking a certain large n limit, different from the one that Sabir mentioned just now, of a field theory where the fields are matrices, are n by n matrices, and so that means that if the fields at each point are n by n matrices, then there's n squared degrees of freedom at each point, and so that's the motivation. And the reason that this class of field theories, I guess I should say, by the way, what I mean by saying that the fields are matrices is not just that there's n squared of them, but further that their interactions can be written down in terms of matrix products, matrix multiplication. So that if I do a rotation, a basis transformation of the matrices, the action is preserved. And with these assumptions, and with the further specification that the operators that we're interested in are ones that are themselves invariant under these basis rotations. So I guess I'm trying to avoid saying that I'm talking about a gauge theory, but the simplest way to make this happen is if it's a gauge theory. So then the physical operators are things like traces of products of these matrices. Then this accomplishes several of the things that we wanted. So one is, which is called large n factorization, is that the correlation functions of these operators at large n are dominated by their disconnected piece, and the connected piece is suppressed by some power of this capital red n squared. And this statement, the statement that some things are nearly statistically independent, is the statement that something, namely the excitations created by these operators O, behaves classically, that they're uncorrelated at leading order in large n. The second thing that it does, which is I guess related to this, is that this is what ensures that in the gravity theory there's some notion of single particle states. So I said that in a CFT the scaling operators don't create particles, but on the other hand, if we just study some ordinary classical field theory in n-to de Sitter space, then certainly if I study some, certainly I can construct wave packets of the excitations of those fields, and so those make particles, and a question that you could have asked is, well, how is it guaranteed that we can organize, and I also said that the Hilbert space of the gravity theory is the same as the Hilbert space of the field theory, and so how is it guaranteed that we can organize the Hilbert space of the field theory in terms of the sort of Fock construction, where you can construct, you can act on some vacuum with some notion of single particle excitations and create more and more particles, and it's exactly this property that at large n these sort of single trace operators correspond to single particle excitations, that you can count the number of traces, and that's the number of particles. And finally, and perhaps most importantly, this red capital N squared appears in the on-shell action. It guarantees that as you take n large, the saddle point becomes better and better peaked. So just within the field theory, this is the case, and so that makes it okay that we're treating the theory classically in the bulk, and only including the behavior at the saddle point rather than having to worry about superpositions of different spacetimes and frightening things like this, which I'm not going to talk about. So okay, and so having said that, this construction where the number of degrees of freedom is of the form an integer squared is I guess it's the best understood class of examples. People do know how to construct examples where the number of degrees of freedom goes like an integer to a power other than 2. Now, to some extent, I guess 3/2 is a popular number these days. And so I'm just going to write n squared just to remind ourselves. And okay, another question that you could have asked is, well, what's the Hamiltonian? What is a description of a field theory where we really know something about the gravity dual? And so I don't want to say too much about this, but just in the interest of giving you some idea about one benchmark example where we know some precise things, let me just mention that there is a certain family of 3 + 1 dimensional superconformal field theories which go by this name, where S is for super, and Ym is for Yang-Mills, and the action. And so there's a nice Lagrangian for this theory, and the degrees of freedom are some gauge fields, some 6 scalar fields. So SUN gauge fields, 6 scalar fields in the adjoint, and 4 Weyl fermions in the adjoint, and these, so they have kinetic terms, and then There's some self-interactions of the scalar fields. So notice that everything is written in terms of matrix multiplication. And there's some Yukawa coupling. And there's this coupling G here, which appears in these interactions, which is the gauge coupling. I've scaled it out of the gauge kinetic term and put it in the interactions. And sort of ruinously for the understanding by string theorists of the renormalization group, this theory is a fixed point for every value of G. And so it's led to this situation where people think coupling constants are numbers that you get to pick rather than things that evolve with scale. But in this case, in this theory, it's true. And so this theory comes with two parameters, which I guess I've already mentioned their names already, so I'm glad I'm doing this. One of them is the coupling constant, which this particular large n limit that we're instructed to take by a Tuft is where we combine the coupling constant and n, that's the other parameter, the number of colors, the rank of the gauge group. So if we're instructed by a Tuft to combine the coupling constant and n into this combination and take the limit where n goes to infinity, holding fixed this Tuft coupling. And so this guarantees a nice structure of the 1/n expansion, which is the thing I skipped in my slides from the first lecture. Notice that this requires taking G to 0 as you take n to infinity. Okay, and the precise statement of the duality is that this theory at arbitrary n and arbitrary lambda, there's a lot of evidence that this is equal to type 2b string theory. That's a particular kind of string theory with some decorations. In ADS5 times S5, where the parameter n, not surprisingly, from what I've said, plays the role of h bar, and 1/n plays the role of h bar, the string coupling, the parameter that controls how often the strings split and join, if you like, and where the parameter lambda is encoded in the size of both the n to de Sitter space and the sphere. They're of equal. They have the same radius. And so,
sorry,
yes.
so you're saying that lambda is related to the radius of ADS.
Yes.
And do you know more or less what is this relation?
Yes. Do you want me to tell it to you? Okay, I'm not going to say it if you don't want to know. I know what it is, and you can look it up. Yeah. So I'm feeling guilty. No, I'm not going to do it. I'm not going to tell you. All right. There's a 4. There's a ton. Okay. So large n makes the gravity theory classical, and strong coupling that is large lambda makes the geometry big. And so it particularly it improves the derivative expansion in our effective theory of gravity, and allows us to, if we wish to take large lambda, it allows us to ignore the effects of string theory. It allows us to ignore the stringy excitations. Okay, and so this statement, type 2b strings ... specifies some specific lists of bulk fields and some specific interactions between them. Right, so this is one very precise specification, thanks to a lot of work, of what the ... is in that theory, that Lagrangian for the theory of gravity that I wrote down last time. I'd like to emphasize that this is one family of examples out of infinitely many other such examples of dual pairs. Earlier I expressed a reluctance to put a measure on these things, but if you ask me how different the examples are, I would have to say not very different, in the sense that the examples where we have some level of detail comparable to this one also involve gauge theories with large numbers of colors and some matter fields charged into that gauge group. Okay, so that's the end of the interlude about where I tell you things from string theory. Let's get back to the construction of this dictionary, of this holographic dictionary, and let's see what we can figure out, again, without appealing to the sort of microphysical quantum gravity kinds of things. So I said earlier that there's a scalar, there's a field in the bulk for every operator in the field theory. And so that's a strong statement. Because if in general, if you think about a field theory, you can construct a long list of operators just by starting with whatever letters you want to call the fields and then multiplying them together and differentiating them and doing things like this. And so it's useful. Let's try to organize this a little bit. So first of all, the operators in the conformal field theory, not surprisingly, form representations, can be put into representations of the conformal symmetry. So we can label them by their scaling dimension and organize them into towers of descendants by generators of the conformal group. That is done by studying fields in anti-de Sitter space in the dual. Secondly, the single trace operators, as I mentioned, is what gives us a notion of single particle states in the bulk. What I mean by this is it gives us a notion of elementary fields. So anytime anybody says the word elementary or fundamental or anything like this to you, you should, look at them like they're lying, right? You should you should worry. I guess that's what I mean. And so, what I mean by that is the word elementary, in my understanding, always makes reference to some weak coupling limit. So that is, if you say that something's elementary, you have to say elementary with respect to some sort of limit in which there's decoupling, and the notion of elementary field. So when I say there's a metric, there's a scalar field, there's a gauge field in the bulk, what I mean by that is that in the large n limit, these fields are free, and so the Hilbert space is constructed by acting with the excitations of these fields on some Fock vacuum. And that's dual to the statement that I can construct states by acting with products of single trace operators on some conformal vacuum in the field theory. Okay, and then there are a few examples of elements of this dictionary which are fixed by symmetries. So for example, if our field theory has currents, has conserved currents, so that is something with a Lorentz index, then that must be dual, since we're going to add a term to the action that makes a source. So this is the operator in the field theory. This thing here is the source that we're going to add to our Lagrangian to compute correlation functions of this current. And we want our action to preserve Lorentz invariance. And so these things, and this source here, I told you, is the boundary value of the bulk field. And so it had better have the complementary index structure, and so it had better be something with a single index, and well, obviously that must be a gauge field, and a result which is not too hard to check based on things we'll say next is that the particular case where the gauge field is massless, so there's actually a gauge symmetry, is dual to the case where the current is conserved. And then along similar lines, any field theory has a stress tensor, because you can put it on some curved space and ask how it responds. And so the field in the bulk to which the stress tensor couples must be the boundary value of some 2-index tensor, which, obviously that's the metric. Okay, so the energy momentum tensor in the field theory corresponds to the metric. A global current in the field theory corresponds to a Maxwell field. So I wrote different indices here because these indices are Lorentz indices in the Minkowski space on the boundary. These indices are indices in anti-de Sitter space, which has one extra dimension. In each of these cases, there's some sort of gauge symmetry that you can use to fix away the extra component. So that's not really a difference. A featureless operator in the field theory, something which is a scalar bosonic operator, corresponds to a correspondingly featureless operator in the bulk, some scalar field, and an operator which has quantum numbers of a fermion had better correspond to some kind of fermionic field in the bulk. Okay, and so as I've said, boundary conditions on the bulk fields correspond to couplings in the field theory, right? We can think about these sources that we're adding to the action as, you could just forget about the sort of action that we were perturbing and think of the whole thing as just some sum of sources. The boundary conditions of the field, therefore, correspond to the couplings in the field theory, the coefficient of a given operator in the Hamiltonian of the field theory. And so in particular, the boundary value of the bulk metric specifies the space, the metric of the space in which the field theory is living. And notice that different couplings in the bulk action. So far I've been talking about the field theory action. So now if I ask, what happens if I change the couplings in the bulk action? So like change the Newton's constant, change the mass of the scalar field. This is a much more dramatic, much more different difference between the boundary field theories. It's because we've already exhausted the changes we can make in the field theory by changing the action of the field theory. So changes in the bulk action correspond to really different field theories. So for example, one change we can make in the bulk action is changing Newton's constant. I've already told you that Newton's constant in units of the ADS radius determines n. And so L to the d minus 2 over g Newton is equal to n squared. And so changing g Newton at fixed ADS radius is changing the number of colors of the gauge theory, right? So it's a much more different difference. Okay, the next goal is to write some equations whose purpose is to confirm this interpretation of the extra dimension as the radial evolution. Okay, and so to illustrate the machinery. Okay, if you I'm going to have to exert some exercise some judgment in deciding how many of the equations to belabor. So try to give me some feedback about how bored you are. So we'll see. So how to calculate? So this is the sort of fundamental equation that the theories are the same, so their partition functions should be equal. In the field theory, this is the thing we want to know. In the bulk, we evaluate the partition function in the only way we know how, in the classical limit by saddle point. So more explicitly, okay, the sources are encoded in these boundary values of the fields. We need to solve the bulk equations of motion here, subject to those boundary conditions. Actually, I need to refine the statement a little bit, as some of you, I'm sure, are eager to complain about this equation. I'm going to fix this in just a moment. In setting up to do this, remember that when we were counting the degrees of freedom this morning, we ran into some ultraviolet divergences associated with the behavior right near the boundary of ADS. And so in anticipation of encountering the same kinds of problems, let's put in the same kind of cutoff that we put. Oh, I got cut off again. Yeah, there's an epsilon there. Okay, the cutoff got cut off. And so as a simple example to get our hands dirty, feet wet. There's some to start doing things. Let's think about a scalar field in the bulk. Hands wet. What is the expression? To get our feet dirty? No. Okay, I'm sorry.
Expressions confused, I think is the expression.
Say again?
Expressions confused.
Expressions confused, yes. To get our expressions confused, so let's consider an action like this. So there's a kinetic term for the scalar field. So this square root of g is to make everything covariant under coordinate changes. This is how to write a kinetic term for a scalar field in curved space. It has a mass term. It has some self-interactions. And I've put this incredibly fancy k here. It's mathfrak k. It's a normalization constant in front of the action. And I'm going to assume that we can, in addition to treating the gravity theory classically, we can also treat the scalar field classically. And so that requires that this thing is big in some units. And so in particular, let's just assume for definiteness that it's proportional to the big red n squared. And okay, so let's to further specify, let's think about the case where this field is propagating in anti-de Sitter space. So really the ground state empty vacuum of a conformal field theory. So in that case, the square root of g, the square root is a determinant of the anti-de Sitter space metric, which is this. I've set the ADS radius to 1 here, but not here. Is 1 over z to the d plus 1. This should be z over L squared. And we're going to study fluctuations of the scalar field around a particular saddle point. A particular saddle point of the whole system, which is gravity coupled to the scalar field, which is the case where the metric is ADS and the scalar field is 0. All right, so that once you believe me that ADS is a solution of the equations of motion without the scalar field, then with this action for the scalar, phi equals 0 is a solution of both the scalar field equations of motion, because they're homogeneous in phi, right? There's a phi in every term. And if phi is 0, then the stress tensor for the scalar field is also 0. So that's a saddle point of the whole system. And okay, and the reason we're going to do that is because suppose we wanted to compute the 2-point function of the scalar field, of the scalar operator. We would remember this partition function. Which let me point to this equation again. The partition function of the field theory in the presence of the sources, which is this, yeah. So we're adding a source phi naught for the operator O, is e to the minus n squared times the on-shell action evaluated on the solution. And to compute the 2-point function, we would differentiate this thing twice. We would differentiate the log of this twice with respect to phi naught, and then evaluate it at phi naught equals 0, right? To compute the partition function in the solution corresponding to phi naught equals 0, we set phi naught equals 0 to the end. And so we only need to know log z to quadratic order in phi 0, right? Because we're taking 2 derivatives and setting phi 0 to 0. And that means that we can ignore the interactions of phi. We can just study small fluctuations, ignore the self-interactions. And so in anticipation of what's about to happen, so we're going to want to evaluate the on-shell action, evaluate the action on the solution. So it's useful to integrate this thing by parts, in which case the bulk term becomes something proportional to the equations of motion, right? If I vary phi to compute the equations of motion, I'll get, this will be delta phi times this, which is the equation of motion. It's just the wave equation in the bulk for a massive field in curved space. And the integration by parts costs a boundary term. So this is a term which is something like phi d phi evaluated on the boundary of ADS. And the reason I wrote this is because we learned 2 things. One is we learned the equation of motion for the small fluctuations is just this wave equation. So underline means it solves the equation of motion. And secondly, we learned that if the field solves the equation of motion, then the on-shell action, which we care about because the partition function we want is e to the minus the on-shell action, is just given by the boundary term. Okay. So the next thing we can do is prove this equation that I mentioned earlier, which we can do just by studying the wave equation near the boundary. So the system we're studying is translation invariant in time and space. So let's use Fourier modes. So let's plug in for our, let's assume that our field, everything is linear, we can do one Fourier mode at a time, is just a particular Fourier mode times a function of z, and plug that into the wave equation. The explicit form of the wave equation gives a term coming from the spatial derivatives, a term coming from the radial derivative, and the mass term, and plugging in the form of the ADS, the particular form of the ADS metric, G inverse is just z squared. 1 over G squared of G is z to the d plus 1. This thing is this guy. And okay, and so that's the wave equation, just using the form of ADS and Fourier decomposition. And now let's look at the behavior near the boundary. So near the boundary is where z equals 0. That's this UV boundary event of de Sitter space. That means we can ignore this mass term. Notice that this equation has a scaling property. That is, except for this mass term, this thing scales like z squared, and this thing scales like z to the d plus 1 minus 1, that's d, and then minus d plus 1 altogether is equal to z squared. Wait, I think I left out that minus 1. Altogether it should be z squared. What happened? No. Sorry. I said that wrong. The k doesn't, this thing is subleading. Wow, okay, sorry. If we ignore the k term, which we can do because z is small, then this term scales like z to the 0, and this term scales like z to the 0. And so there are power law solutions spoiled by this. Okay, it says it there. By the k term. And so making an ansatz that the function is a power law and plugging it in, we find a solution if the exponent, which I, in anticipation of its future interpretation, I call delta, if the exponent satisfies this equation, relating this exponent to the mass. Notice that the momentum does not appear here. Yeah. the scaling dimensions usually don't depend on the momentum, right? That's a weird thing. And so the two roots of this equation are of this form, which that looks like this in the space of delta versus m squared. So notice for a fixed mass of the field in the bulk, there are two solutions for every value down to some special value, which is called the Brighton-Lohner-Friedman bound, which is where this discriminant goes to 0, below which there's nothing. There's no real roots below there. Okay, so a few comments. The solution that's proportional to delta minus, which is the one where we take the minus here, is always the bigger one. That is, z to the delta minus is bigger than z to the delta plus when z is small. And so usually we interpret this as the source, in the sense that it's the term in the behavior of the field which is bigger, and so we think of it as the thing that we hold down. And then the smaller thing is the response. The other one always decays near the boundary. Delta plus is always positive. It's useful to remember that the sum of the roots is always d. Okay, and so it's useful to impose boundary conditions on the differential equation that allows the solution. It's generally not a good idea to do otherwise. And so I have to admit that I lied a little bit earlier when I said that the boundary value of the field is equal to the source. Rather, the boundary value of the field should be the source times some appropriate power of z, which is determined by this answer. And okay, and it's useful to think of this in the following way. Think of the field near the boundary as at this cutoff surface that we mentioned as being the source times some multiplicative renormalization of the source. So this is some cutoff dependence which is determined by the scaling dimension, and so think of this as some cutoff independent renormalized source. Okay, and so with this notion of multiplicative normalization, we can think about this term that we're thinking of adding to the boundary action, which is the source times the operator in the field theory, and think about literally evaluating this on this cutoff surface. So that's what makes this a little bit heuristic, in that I'm combining bulk notions and boundary notions here. But so evaluating this metric on the boundary, that gives this factor of L over epsilon to the right power, and relating the source to the renormalized source that we introduced previously. The operator itself has some scaling dependence, which is what encodes its scaling dimension, and then demanding that this whole thing be cutoff independent, and therefore finite when we take the cutoff to 0, tells us how we should scale the renormalized operator, and in particular it tells us that it scales like the cutoff to the delta plus. So that is, we should interpret delta plus as the dimension of the operator.
John,
Yes.
it's maybe an annoying point.
Okay.
Don't you need counterterms for this?
No. I mean, to make the whole action finite, yes, but to make that term finite, no.
But I mean, phi 0 renormalized could depend on the counterterms.
You're saying that there may be some other hidden cutoff dependence besides
In fact,
this.
it usually probably depends on that counterterms.
The boundary behavior. I think that, well, so if our goal is so my goal here was just to give a heuristic argument for why we interpret delta plus as the scaling dimension of the operator. And so for doing that, I think specify more about what source I'm thinking about. And I think by doing that, I could find a situation where I can ignore this. I'll say a little bit about counterterms.
Sorry for annoying you then, but
I forgive you. Yes, no, this is the holographic normalization is an important and complicated subject. So to really be convinced that we should interpret delta plus as the dimension of the operator, we should really compute the 2-point function and see that it scales in the right way with this particular delta plus. And I'll outline how to do that in a bit. One small comment is when the mass squared is small, I guess by small I mean negative, there's something called alternative quantization, which is another CFT that you can make from the same bulk theory with different boundary conditions. And that's in this window here, where there are two branches of this solution, where the dimension of both of them is big enough, let's say, and the way to construct this other theory is just by changing your mind about which of the two things you think of as the source and which of them you think of as the response. Okay, roughly it's imposing Neumann boundary conditions on phi instead of Dirichlet boundary conditions. Okay, so let me make some comments about relevantness, which are visible from what we've learned so far. So the dimension, these dimensions have this form. Notice that if m squared is positive, then delta, which I said is in the usual quantization, is the dimension of the operator, is bigger than d. And that means that the operator, the corresponding operator whose dimension this is by definition an irrelevant operator. Right? Its conformal dimension is bigger than the space-time dimension, so if you add it to the action, integrate it over space-time, it's something which flows to 0 in the infrared. So that is, the term you add to the action is of the form some mass scale, right, which you pick when you add it to the action, to some power which is negative times the operator. And so the effects of such an operator go away in the infrared, where energies are less than this mass scale. And the coupling that appears here, and which goes to 0 in the infrared, is the field in the bulk. So the profile, the behavior of the field as it evolves in the radial direction away from the boundary is the coupling, in the sense that towards the UV it gets bigger, and towards the infrared it gets smaller. Notice that in this case, if phi naught, the perturbation that we're making here, is finite, that means that at the cutoff it has some size. If you moved the cutoff closer to the boundary, it would get bigger and bigger. And so, as you take the cutoff to 0, its perturbation becomes infinite, and it's no longer sensible to treat phi naught as a small perturbation. So that is, its back reaction will change the UV behavior of the metric. It'll destroy the fact that the thing is a conformal field theory in the UV. This is the dual of the statement that if you try to add irrelevant operators to a normalization group fixed point, you need to do something else. You need to add information. Right? You need to say, that is, this is what people mean by non-normalizable. Right? You need to add extra information to say where the flow came from. Okay. In the case where the mass squared is 0, delta equals d, that means that the operator is marginal. In the case where m squared is negative, that is, the field in the bulk is a tachyon. That word is meant to instill fear, but it's actually not something to be scared of, because for some reason it's okay. Right? We just did the analysis of the quadratic fluctuations, and we didn't find any kind of instability. In fact, what it means is just that the dimension of the operator is less than d, and so the operator is a relevant operator. The reason that negative mass squareds are okay if they're not too negative in anti-de Sitter spaces is that we're fixing a boundary condition on the field and at the UV end of the geometry. And so if the field tried to roll down its potential hill to improve its energy by realizing that it's living on top of a hill, it simultaneously has to pay a price of making some gradient energy between its value in the bulk and its value that we're fixing at the boundary. And so only if it's really, really beneficial to the field to roll down the hill will it take advantage of that. And the place where it becomes beneficial is this Breitenloner free mid value here. Okay. Okay. So so far we've put together some ingredients in the calculation of 2-point functions. I'm going to say a little bit more about it. And I need to specify a little bit about which 2-point function I'm talking about. Let's consider for a moment the case of the Euclidean theory. So in that case, I guess I've been writing Euclidean things. I've been writing that the partition function is e to the minus the action, right? That's a Euclidean formula. And so let's think about the Euclidean 2-point function by thinking about the scalar wave equation well, I've written it in momentum space. So to make it Euclidean, all you need to do is pick this k squared to be positive. Right? So it's either Lorentzian calculation with Euclidean momentum, or with space-like momentum, or the Euclidean case. And the solution of this equation is Bessel functions. All right, so Mathematica can tell you this. There's two linearly independent solutions. It's a second-order differential equation, and the two solutions are Bessel k and Bessel I times some powers. And the asymptotic expansions of these Bessel functions near the boundary, which is a regular singular point of this differential equation, matches the analysis that we just did that I messed up, where we got these power laws, which were z to the delta plus and delta minus. In the interior of ADS, where z goes to infinity, these two Bessel functions behave. Bessel k dies exponentially, and Bessel I grows exponentially. And so, if we want this analysis to make sense, if we want to find a regular solution of these equations, which is within the regime that we're thinking about, where the phi is a small perturbation, we had better set to 0 the coefficient of the Bessel I, which blows up in the interior. And this is a representative example of what always happens in Euclidean calculations, which is that regularity in the interior of the geometry uniquely specifies one of the integration constants. So we had two integration constants because we had a second-order differential equation. One of them we can think of as being fixed by the source. The other one, in this case, in Euclidean case, is uniquely fixed by regularity. Okay. There is this general statement about Euclidean regularity uniquely determining like half of the integration constants also extends to a nonlinear version, which is called the Gram-Lie theorem, which is a very fancy theorem, which makes the same kind of statement not about a single free scalar field, but about the metric. It says that It says that if we pick a metric near the boundary of ADS in the Euclidean case, so that in the Euclidean case, which is sufficiently close to the let's say the flat metric, then that is not too bumpy, then there's a unique constant negative curvature metric that is a solution of the Einstein's equations with negative cosmological constant with those asymptotics. And I guess the initial choice of the metric is only well defined up to conformal equivalence. But so that's exactly analogous, nonlinear version of this statement for the gravity case. That is just demanding that it's regular in the interior specifies the solution.
Excuse me?
Yes.
Sorry, before I wanted to ask, the fact that you allow for a solution with a negative square mass means that you naively will have tachyons. But they are not really tachyons because the space is expanding and therefore they don't violate causality.
There's no instability. Oh, sorry.
It's about causality, not about the stability.
There's no issue with causality.
Because the space is expanding and therefore they're not real.
There's just no issue with causality at all. Yeah. I mean, negative mass squared means usually an instability, right? It means that the ground state, the state that you're expanding around is unstable and that the field will roll down the hill. But it doesn't roll down the hill in a de Sitter space.
But then it also means that it can travel faster than light?
No.
There's an effective mass which is positive.
Okay, yes. But that is because it is embedded in the gravity.
Through the coupling to the curvature of the gravity.
Yes.
Okay. So I'm going to skip the next few slides. Their purpose is to analyze the behavior of so we found the solution of this wave equation. By analyzing its behavior near the boundary, we can extract the two-point function very precisely and see that, in particular, that it goes like 1 over x to the 2 delta, where delta is delta plus the root that I claimed was the scaling dimension. So I think it's not nice to subject people to this kind of expansion of Bessel functions. If you want to think about it, you can ask Mathematica about it. You can look it up in grad student in Rijik, or you can look at my slides. But yeah, so the conclusions of this calculation are the following. It's pretty simple, but it's a little tedious. So first of all, the ADS radius appears only in the overall normalization of the answer. Where did I write the normalization? I should have written the whole answer somewhere. Well, okay, that's a true statement, and it only appears in the combination ADS radius this ADS radius to the d plus 1 times this normalization constant, which I said was n squared. So actually, it's this whole the whole thing should be n squared. There's a multiplicative renormalization will remove this cutoff dependence, so that's exactly the multiplicative renormalization that we motivated by this heuristic argument. And then there's a further additive renormalization which is necessary, which in the calculation that I just elided, one finds in addition to this interesting power law fall off in the separation between the two insertions, also contact terms, also terms which are independent of the separation between the which are only supported, not independent, the opposite, are only supported when the operators are on top of each other, and which are very sensitive to the cutoff, and a construction which removes these things from the answer in a way that so you don't ever have to think about them, is called holographic renormalization, and it's exactly the dual of ordinary counterterm renormalization in field theory, in that we think about adding to the bulk action a series of local in the boundary intrinsic terms in the boundary theory. So meaning terms made only of the fields at the boundary, not their canonical momenta. And the particular term that you need to add in this case to remove the cutoff dependence is just phi squared times some coefficient which is fixed. And so adding terms like this affects neither the bulk equations of motion nor the behavior of the two-point function at finite separation. And so it's only, you only need to worry about it if you're really worried about this, constructing a formalism where the cutoff never appears and sullies your eyeballs. All right, so that's okay. So that was a Euclidean calculation. Euclidean calculations are useful. If you understand them well enough, you can use them to make real-time calculations. It's not always the best situation to have to be in. Sometimes it's useful to be able to directly calculate real-time things. And so it's useful to have a prescription to do that holographically. When writing down the wave equation that we wrote down that in de Sitter space with Lorentzian signature, so one encounters an interesting thing when the momentum is time-like. So that is when the frequency is bigger than the momentum, which is that this nice property that in the Euclidean section, one of the solutions was good and one of the solutions was bad, breaks down because all of the solutions in the far infrared behave like plane waves. This isn't too surprising because the geometry of the metric in the far infrared is just flat space. And so if you think about the behavior of the scalar wave equation in flat space, you'll convince yourself pretty quickly that the solutions are plane waves. And so that's what's happening here. And so, and by the way, this region of de Sitter space is called the Poincare horizon. So the solutions oscillate. And so that makes it kind of hard to say which ones are good and bad because they're all just wiggling. And in fact, there is no good and bad, as in many situations. This ambiguity reflects the fact that there are many different real-time Green's functions which are interesting for different purposes. An important example, which I'll focus on, is the retarded Green's function, which describes the causal response of the system to some source. Okay, the next two slides I'm also going to skip, which are a review of linear response theory. Everybody knows about linear response theory, right? I see some interesting dance of yeses and nos. Okay, let me just summarize the content of these slides. It's just to say that the retarded Green's function, which by definition is the two-point function of the commutator of an operator and another operator at different times, multiplied with a heaviside theta function, which says that one of them appears after the other one, can be related to the change in the expectation value of one of the operators, which I called A, in response to adding to the Hamiltonian another one, the other one. And so why exactly it's the commutator is the subject of the next few lines. I'm going to leave that as homework. An example of a situation where you might care about this is, for example, in thinking about conductivity of transport, in which case one of the operators we can think of as the perturbation we can think of as an external electric field. The operator, therefore, is just the current. The thing we measure is also the current, and so the thing in this case we're interested in is the current two-point function, the current retarded two-point function, and combining this with Ohm's law, J is sigma E, says then with the formula we just derived implies this Kubo formula, which relates the conductivity to this retarded current of Green's function divided by I omega. So how do you compute the retarded Green's function holographically? The thing you want to do is find some boundary conditions which describe boundary conditions in the infrared which describe things that happen as a result of a perturbation, and so you won't be too surprised to hear that something that happens is things fall into a horizon, a future horizon, and don't come out. And so the right boundary conditions to impose are boundary conditions which are where the stuff is going into the horizon. In the case that we were just talking about, this choice is the one that looks like this, so that in particular there's a relative plus here between the time dependence and the z dependence, so that this is the wave front of this plane wave moves towards larger z as t grows, and the combination of those Bessel functions that behave this way, I think, is this one. I've gotten that wrong in the past. I think this is the right one. So this same prescription adapted to a black hole horizon rather than this zero temperature ADS horizon works in the finite temperature case. Okay. And then what do you do with the solution? So so suppose we find a solution of this wave equation with the right boundary conditions in the infrared, with the right boundary conditions in the UV. The boundary conditions in the UV say that near z goes to 0, it behaves like, there's one linearly independent solution that behaves like this, like z to the delta minus times some function. Added to that is another linearly independent solution that behaves like the other exponent, times phi 1. And if I tell you I have a solution which satisfies the right boundary conditions of the infrared, and has this expansion near the boundary, this defines this coefficient phi 1, think of it as the subleading behavior of the solution. And these two functions have all of the information about the Green's function, in a way I'll explain in a second. One way you could imagine finding it, at least in the Euclidean case, is plugging this solution into the on-shell action that defines W, so just W is minus log Z. And so then you could imagine differentiating it, but this formula is a Euclidean formula. In the Lorentzian case, there's some i's, right? It's e to the I times the action that appears in the Lorentzian partition function. You have to do stationary phase and not a saddle point. It's a little tricky. The following trick avoids that difficulty. Okay, everybody remember the time when you read Landau Lifshitz Mechanics. Right? Think about this. There's a part in there which explains the following. Maybe it's possible to learn this from some other source, I'm not sure. But there's a part in there which says the following thing. Think about a particle in one dimension with an action which is integral over time of some Lagrangian. And imagine we're interested in the propagation of the particle between an initial time and a final time. And and so you can imagine evaluating the action for each path with some fixed initial boundary condition. So x of ti is the value of the position of the particle at the initial time. And we can ask, and you can imagine also fixing some boundary condition here. But let's ask, what is the variation of that action with respect to the initial value? So I wiggle this point and ask how much does the action change? And something that you'll recollect if you think about it for a few minutes is that that's equal to the canonical momentum at the initial point. So yeah, you have to think about it a little bit, where the canonical momentum is just this useful thing. Okay, so it has the right dimensions, right? Okay, I'm not going to derive that, but you'll see that a slight generalization of that statement to our situation tells us what we want. Because you see, think about the analog of this x as the field in n times de Sitter space, and think about the analog of the time direction as the radial direction. So then the thing that we want is the expectation value of this suppose we're interested in the expectation value of this operator. You know, if we were doing linear response, so we want the expectation value of this operator to linear order in the source, but it's even better if we can just compute its whole expectation value. So that's the analog so the formula that we have for it is the variation of the on-shell action. So that's W. This is my definition of W, with respect to the boundary value of the field at the boundary coordinate. There's one small difference, which is that actually the boundary is some higher dimensional surface, and there's a value of the field at every point, and so this is actually a functional derivative. But forget about that, just think about a single point. And so then you see this equation then tells us that we can relate this thing that we want, which is equal to this response, to, well, the canonical momentum of the field, modulo 2 minor subtleties. So this pi is the canonical momentum of the field, that is the derivative of the Lagrangian with respect to the analog of x dot. The analog of x dot is the radial derivative of phi. The two minor subtleties are, well, the boundary value of the field is not quite the source, right? There's this factor of z to the delta minus that we had to introduce. This is this renormalized source, and so when we differentiate with respect to phi naught, there's this extra power. So that's what gives that power. And then the other thing is, I think maybe what Julian was worried about, which is that pi itself, this canonical momentum, in general has a term that's proportional to the source that we want to subtract off. So this formula is true. This is a true formula for the response of this operator to an arbitrary source away from the support of the source. And if we plug it in if we compute the canonical momentum in the example that we're thinking about, that canonical momentum is just proportional to phi1, where remember phi1 is defined by this formula, the subleading behavior of the field near the boundary. Okay, and so if we're interested in linear response, this determines the formula for the Green's function.
So if you want to know the response in a region that you're still sourcing,
yeah, then it's a little harder. Then you need to do the renormalization.
You can do it though. By
Yeah.
those extra terms.
This formula is not quite true. You need to fix the formula. Yeah. Costas gave me a very hard time about this.
I bet.
Yeah. Yeah. So, but you know, if the thing you're interested, so that's exactly like the contact terms, right? So if you're interested in the 2-point function, the source is a delta function, right? And so the support of the source is, you know, that's measuring this thing on the support of the source is when you put the two things on top of each other. And so if you're interested in the finite separation Green's function, this issue doesn't arise. But more generally, if your source is some finite thing everywhere where you care about it everywhere, then you need to be more careful about this.
But for conductivity, is that not the case? You're not shaking it everywhere?
You mean if you're like shaking it at some fixed momentum?
Well, you don't usually do that though, right? You usually put momentum to 0.
You mean the DC? Oh, momentum. Oh, I see. So then you're even more shaking it everywhere. Yeah, I guess I should worry about that. I have to think about how to fix it. Yeah.
It'd be safer to repeat the same procedure, but on the fully renormalized finite.
Yes, that's exactly what you have to do. Yes, repeat the same procedure.
To avoid.
Repeat the same procedure after having renormalized. That's what to do. Yes. The formula may not look as nice. You may not just be able to write it in terms of the canonical momentum. Okay, so the summary of this discussion is that the leading behavior of the solution encodes the source, at least in the ordinary quantization. So it's what perturbation you're making of the action of the field theory. And then the coefficient of the subleading behavior tells you the response. It tells you about how the state of the field theory responds to that change. And so a nice picture of this is that you're sending in this excitation, which is the source. What happens in the infrared decides what comes back. That tells you the response. And the Green's function is the ratio of the two. Okay. Notice that there's a special case of this, which is if the source vanishes, but the response is non-zero. In that case, you'll find poles in the Green's function. So it has values for, so suppose we're thinking about the momentum space and frequency space Green's function, then at a value of frequency momentum where phi1 is non-zero, but the source is zero, that means that the system has an actual state, an actual excitation at that energy. And so, yeah, okay, good. So far, we've restricted our discussion to quadratic fluctuations on the grounds that we were interested in the 2-point function. Someday you may find yourself interested in a 3-point function. Who knows? And so in that case, this cubic interaction that I wrote down in my initial scalar field action will matter. But we can still treat it perturbatively in the strength of the perturbation. The equation of motion that we have to solve is just this one, with an inhomogeneous term coming from the equation of the derivative of the phi cubed term. Ignore that. And so we can really do this using perturbation theory. A useful way to visualize this horrible construction with Green's functions for this wave equation is in terms of these pictures. Think of these circles as the boundary event at de Sitter space, and the external legs on our Feynman diagrams correspond to insertions of these sources at the boundary. These wiggly lines which connect the sources from the boundary to the bulk are Green's functions for the homogeneous wave equation. These vertices are places where the cubic interaction takes place. It costs a factor of b. And then propagators, wiggly lines that connect points between points in the interior are Green's functions for the wave function in the wave equation in the bulk. And so in this way you can, in a way which is straightforward but in general quite tedious, construct higher point functions. Okay. A quick comment about the alternate quantization. Maybe I skip this. I don't want to talk about it. If someone wants to ask about the alternate quantization, I will talk about it. Instead, I want to talk about thermal equilibrium. Okay? So far, we've been talking about CFT in vacuum, right? So nothing in the world, everything is scale invariant. Just as an illustration of the machinery, to get a little closer to physics, let's think about finite temperature. So putting a CFT at finite temperature. Are there any questions? I guess it's a good time to take questions. Okay. So like I said, ADS is scale invariant. A solution of the same gravity equations, so something dual to a CFT, in some situation where there's a scale, some perturbation of it where there's a scale, but a scale which is appearing in some perturbation that doesn't break the fact that the shortest distance the thing is a CFT. So that means that asymptotically the geometry should approach into de Sitter space near the boundary. A solution is something like this, where there's an emblackening factor, something which says how quickly time goes in different places, and also some change in this component of the metric. And with a particular function of this form, it solves the same equations of motion. So that's a good exercise for anyone who wants to, what is the expression again? Get their hands wet?
You get your feet wet, and then your hands dirty.
Feet wet and hands
Then
dirty.
your hands wet.
And then you get muddy. Okay, whichever one, so whichever one of those you want to do, check that this solves the same equations of motion as the ADS metric. And notice also that when this emblackening factor goes to 1, it becomes entered de Sitter space again. Okay. On the other hand, instead of z going to infinity without anything interesting happening, there's a special value of the radial coordinate that is a special energy scale where something bad happens, something funny happens, where this emblackening factor goes to 0. That is the origin of the black in the emblackening factor. And in particular, it goes to 0 linearly. And this is a horizon in the following sense. If you study the propagation of light in this background, which is the thing that goes the fastest, here's a picture of time going this way. This is the radial coordinate. This is z equals zh. If you look at the propagation of light, for values of z closer to the boundary, light can travel like this. It can in particular start from somewhere close to z equals zh and reach the boundary, therefore influence the things that are happening at the boundary. But if it starts from a value of z any bigger than zh, it never escapes. So not even light can escape, it's a black hole. I claim that geometries with horizons, in this context and in others, geometries with horizons like this one, in particular where there's a linear 0 of this emblackening factor, describe thermally mixed states. And one piece of evidence for that, Guillaume-Duvallet notwithstanding, is the fact that near the horizon, near z equals zh, the geometry looks like this. I can make a change of variables, which is, that's the point of general relativity. The coordinates don't matter. So I can pick some other coordinates that I like better. Near the horizon, let me define rho squared to be this deviation from the horizon, in terms of which the metric takes this form. And this coefficient kappa is constructed from the slope of the emblackening factor, and it's called the surface gravity. And this is called Rindler space. I can make it look even more familiar if I continue it to Euclidean time. So define a new time, tau, which is related by a factor of I to this variable, in which case the metric takes this form. If I further redefine tau to be, kappa tau is some new time, everybody will recognize this as, what is it called? The plane in polar coordinates. Right? So rho is some distance from the origin, tau is some angular variable. And it's the plane in polar coordinates as long as the angle is correct. So that is, the periodicity of this kappa tau variable has to be the right one. So in particular, it looks like this. It looks like this, unless kappa tau is periodic with period 2 pi. And if there were a deficit angle, that would not be a solution of Einstein's equations. It would not describe a saddle point of the path integral that we're trying to do, because there would be some curvature there. And so this means that the solution which has a horizon, has a Rindler horizon like this. The case where the emblackening factor is linear and is called a Rindler horizon. Is analytically continued from the Euclidean section from a solution which has periodic Euclidean time. And in particular, this identification of the Euclidean time is true everywhere in the bulk, and so it's also true at the boundary. And so that means that the field theory is living on a space with periodic Euclidean time, and I hope everybody will agree with me when I say that periodic Euclidean time means finite temperature, right? The thermal partition function is trace e to the minus beta h. So e to the minus something h is evolution in Euclidean time by an amount something. So then trace is identification. Everybody with me? More nodding. Okay, I'm sticking with that one. All right. Yeah, and so this gives us an identification of the temperature in terms of this surface gravity, and therefore in terms of the location of the horizon. This is also the temperature at which the Hawking radiation will happen. And a more sophisticated analysis, and too much more sophisticated thing, of fields living in this near horizon geometry, this near horizon Rindler space, allows us to compute the local density matrix and verify that in fact there is it is locally a thermal density matrix with this temperature. Okay, I'm not going to do that. Okay, so this is my statement that the identification of tau also applies to the boundary, and so this is the solution that we should use if we want to construct the saddle point of the gravity path integral, which describes the field theory with periodic Euclidean time, that is finite temperature. And so from its properties, we should be able to infer the thermodynamics of the field theory. One thing that I've already mentioned is that a black hole has entropy. It has entropy, which is in an Einstein gravity theory, like the one we're discussing, which is the area in Planck units with a 4. And evaluating this area for the black hole we're studying, it's a little bit of a funny black hole in that its horizon is a plane rather than a sphere, like we're used to in flat space. Its horizon is a plane, which is the same plane on which the field theory lives. So this area is infinite because of the integral over the spatial directions. Let me cut those off by thinking about some finite volume patch of the field theory. And again, this factor of square root of g gives us some L over z to the d minus 1, but now we evaluate it at the horizon. And so this quantity, well, okay. And plugging this in gives this answer for the entropy. It's extensive in the field theory directions, not too surprisingly. And using the relationship between this radius of the horizon and the temperature that we just derived, we get this formula. So this L to the d minus 1 over g Newton is what earlier I called red capital N squared. It's related by the counting of degrees of freedom to red capital N squared. This particular factor of 2 pi is the right answer for the Engels-Forcy-Brewing-Mills theory. So this requires a little further, like this is input from string theory here. You can ignore that factor if you want. And so notice that it depends on temperature, like this power. So the answer is red capital N squared times volume times t to the d minus 1. Once you believe that this thing should be extensive in the volume directions, this power of temperature is determined, right? So this stuff in Boltzmann law that Subir was talking about is a consequence of dimensional analysis, right? Unless but of course dimensional analysis is always true, but sometimes there's some extra dimensional quantities that you forgot about, right? And that's the way that this can be violated. But in this case, there's not, and so this is what we had to get. Notice that the entropy density is this entropy per unit volume, which is proportional to the area density of the black hole. Yeah, I really like that concept of area density. So the point of view on this black hole thermodynamics that I'm trying to emphasize is is that we can compute the thermal partition function of this field theory for which we have a gravity dual by considering the path integral with periodic Euclidean time. To compute that path integral, if it has a gravity dual, we can instead compute the dual gravity path integral and do it by saddle point, in which case we get e to the minus this on-shell action, where this g underscore, the solution of the equation of motion, is the solution of the equation of motion with the correct periodicity of Euclidean time. And so this on-shell action is directly an evaluation of the field theory free energy, which we can compute in this example, and the answer is this. On the other hand, you can also compute the free energy of n equals 4 Brewing-Mills at weak coupling, and the answer there is this. It's a factor of 4/3 bigger. And so the picture from what we know of this is the free energy per unit volume, I guess divided by some power of the temperature, as a function of the Satov coupling is this at weak coupling and only slightly smaller at strong coupling. Okay. A few checks that this makes sense, that this point of view is consistent, is, and if you like, this is really a derivation of this this statement. So here we computed the Bekenstein-Hawking entropy. We computed the entropy of the black hole by using this Bekenstein-Hawking formula. Once we know the free energy is a function of temperature, we can also compute it just using the first law of thermodynamics, right? Just the usual relation in thermodynamics between the entropy and the derivative of the free energy with respect to the temperature. And this is a kind of a non-trivial statement in that the left-hand side here is something that we can evaluate just at the horizon, whereas the right-hand side here involves this free energy, which we get by integrating the action over the whole space-time evaluated on the solution. So this is a pretty strong check. A few other things we learn are this answer for the thermodynamics is of the same form as we'd expect for a conformal field theory of finite temperature. And in particular, it has a positive specific heat. So unlike black holes in flat space, which have negative specific heat and therefore don't just sit there, the black holes in anti-de Sitter space are thermodynamically stable. Okay. One more very important conceptual remark is that a property of thermodynamics of simple systems is that there are only a few state variables, right? There are many fewer state variables than microscopic degrees of freedom, and there's the entropy and the temperature and the free energy and the usual P and V and these things, and that statement is dual to the uniqueness of stationary black holes. The statement that there are only very few different solutions of Einstein's equations which are stationary, which the general class of such things is called no-Hare theorems. Okay. I guess, let's see, how are we doing on time? Let me make a few comments about evaluating the on-shell action. So one thing I just said was that we could evaluate the on-shell action and get some nice answer, which I wrote down. There's some information behind that which I think is worth sharing, which is that also in this case we have to add some boundary terms. We have to add some boundary terms of two classes. One of them I've written as S counterterm is of the same class as the counterterms that we added earlier to cancel the contact interactions. So these are local intrinsic terms that depend only on the fields at the boundary, not their canonical momenta. And in particular, to get a finite on-shell action, the thing we have to add is just a boundary cosmological constant. So integral over the boundary, covariant, a number. This gamma is the metric at the boundary. There's another kind of boundary term. There's another kind of boundary term, which is the Gibbons-Hawking term, which I guess I feel a little uncomfortable coming here and explaining it, but let me nevertheless try, which is analogous to the term which I would have had to talk about if I wanted to explain the alternate quantization, which I skipped. So it's a term which depends on the derivatives of the field in the radial direction to the boundary. And so in particular, it changes the nature of the boundary value problem. And in this case, its introduction is motivated by the desire to be able to write the bulk action in terms of first derivatives of the metric. So in particular, integrating by parts the Einstein-Hilbert term in the bulk to get the equations of motion produces Einstein's equations plus a boundary term. And if we want to solve a problem of gravity in the bulk with a Dirichlet boundary condition, which is what we're doing when we say the metric on the boundary is flat space, right? That's saying that I want the metric in the bulk to approach some metric that I'm specifying, so it's a Dirichlet problem in that sense. Then I want to study a variational problem where I don't vary the metric itself. And that means I allow its derivative to vary. And so the role of the Gibbons-Hawking term is to cancel this term in the variation of the action with respect to the field. The Gibbons-Hawking term is constructed from just the extrinsic curvature of the boundary metric, which can be written in this way. Okay. So, and another payoff of this slightly technical comment is that it allows us to compute the expectation values of the stress tensor in a very direct way, just as an example of this general prescription for computing correlation functions. So the stress tensor, remember, is the operator whose source is the space-time metric. And so if I want to compute an expectation value of the stress tensor according to this basic equation of ADS-CFT, the thing I should do is evaluate the bulk action and differentiate it with respect to that source with some factors to make it covariant. And so this formula is just the same formula for relating expectation values in the field theory and in the bulk. And with these counter terms that we just added, we get a finite answer when we do this. And in particular, it satisfies the Ward identity for scale invariance, which is that the trace of the stress tensor vanishes modulo anomalies, which come from curvature. And in thermal equilibrium, if we evaluate this on this black hole solution, we get an energy and pressure which satisfy this this equation of state, which is this formula evaluated on the stress tensor. Okay, so in the last couple minutes, so I want to move very slightly away from equilibrium, and you can stop me if you want. Okay, so far I've described a bulk description of equilibrium. You might ask, which I said it's a black hole, and so a very natural slight elaboration of that is that the approach to equilibrium from some non-equilibrium state then is very naturally thought of. The inevitability of the approach to equilibrium is then very naturally thought of as being dual to the inevitability of gravitational collapse. So that is the arrow of time in the field theory, which says that if we let start in some random state and let it go towards equilibrium, that it does so. Sorry, if we start in a random state and let it goes towards equilibrium, is dual to the statement that that stuff falls into black holes. Yes.
Ask a question. So you really motivated the Euclidean black hole being
Yes.
field theory, and finite temperature equilibrium field theory is no harder than normal equilibrium, normal field theory. But real-time dynamics in finite temperature field theory is sort of a step harder from a boundary perspective. But from the bulk perspective,
like in perturbation theory.
Yeah, for example. But from the bulk perspective, it's trivial.
Okay.
Maybe I can ask a question instead of.
You're saying this is an opportunity to say something positive about the duality.
That's certainly true. What's the evidence we have that real-time finite temperature dynamics is just the Lorentzian black hole dynamics in that background? The Son-Staranets description is that.
You're asking me why I should impose ingoing boundary conditions to compute the retard?
Yeah, or how we can prove that this is the correct way to treat boundary field theory.
Oh, okay. Yeah, so I sort of skipped that. So right. I guess, okay, since you say the word prove, I'll bring out the heavy artillery. So as you know, the way to sort of systematically compute real-time dynamics in a finite temperature field theory, and even out of equilibrium, is using Keldysh, which involves complexifying various things and studying contours of integration, which move off from the real-time axis. And I guess maybe the best evidence for this prescription is that you can construct the dual of the Keldysh prescription. So given some specification of a Keldysh path integral, you can use that to construct the boundary conditions for and for a theory with a gravity dual. You can use that to construct the boundary conditions that the metric should satisfy. And in the case where the thing you're doing is just linear response with causal boundary conditions, it turns into this ingoing prescription.
But only in the linear regime.
No, I think it's It's also true. I think it's also true for higher point functions near equilibrium.
I don't know.
You don't think it's true? Let's see. The derivation that I'm thinking
I
of.
mean, you
just
can get
does
all
two
this
functions.
Kelder stuff to some extent from the Euclidean one by the right continuation.
Yes, that's also true.
But this Graham-Lee theorem does not just have an easy.
Oh. No, I
That's
wasn't
the
thinking of
subtle
that. No, I was thinking of. So that's really a finite deformation, like big.
Right. Right.
No, but
that's
sorry, I
why
just-
real-time dynamics is a lot harder, but just linear response is not that much harder.
I guess I was thinking of just multiple point correlation functions in equilibrium as a
Near
function of
equilibrium.
time. Yeah, near equilibrium. I think that for that, if there's a proof. But yeah, I think you're right that if you ask for something arbitrarily far from equilibrium as a function of time, then
Then the Euclidean case is vastly different from the Lorentzian.
yes. But actually, okay, good. So this is a useful comment to make, though. So we're used to thinking of real-time dynamics and finite temperature as like something kind of hard and confusing, where there's like omegas and complex numbers and all these horrible things, and that seeming horror is a price that we're paying for trying to take advantage of translation invariance. Right? That's the reason we work in frequency space and momentum space. But if we just forget about translation invariance from the beginning and just think about everything in real time and real space, the fact that Einstein's equations are causal just completely obliterates this problem. There's just no issue at all. So for example, if you were going to like solve some far from equilibrium problem by numerically integrating Einstein's equations with the right boundary conditions with some time-dependent horrible sources and things, you just don't have to think about it. Einstein's equations are built to solve this problem. It's just not a problem. Yeah, so that sort of is some small disincentive for worrying about like the niceties of those Keldish prescriptions. Yeah. Okay, so having said that, let me say a little bit about far from equilibrium things. As I said, the arrow of time, the fact that there's an approach to equilibrium, there's dissipation, is dual to the statement that stuff falls into the black hole and doesn't come back. So saying that it falls into the black hole, which already existed, sort of presumes that I'm talking about some situation where I'm near equilibrium and then I perturbed it. But people have by now done quite a bit more dramatic things. I guess my favorite class of examples is the constructions of Paul Chesler and Larry Yaffe, where I guess one of the first things they did was they study a case where we start a field theory into de Sitter space, and then this is a picture of one of the components of the boundary metric, which is something we get to pick as a function of time. And at some time, they suddenly kick it, and then they watch what happens. And the thing that happens is that it forms a black hole in the bulk, and they can watch the approach to the equilibrium thermodynamics, and they've learned some things by doing that. Okay. Another example of a near equilibrium quantity that you might be interested in, which I'm not going to explain, is the shear viscosity, which has received a lot of attention. And and this is an outline of a calculation of it, which I'm not going to do. So I didn't calculate the value of a hydrodynamic transport coefficient of this plasma that you make by putting a CFT at finite temperature. More generally, you could imagine studying not just small fluctuations, the hydrodynamic fluctuations, but actual, real finite nonlinear hydrodynamic flows. And I guess Shiraz is going to spend a whole lot of time telling you about this remarkable fact that solutions of Einstein's equations of a certain form that we get by taking a black hole in ADS and locally boosting its horizon correspond to solutions of Navier-Stokes equations with particular transport coefficients, namely the ones that we would have computed if we had thought about those the previous slides. And so this is an amazing thing, which I guess Shiraz will tell you about. Personally, I was a little disappointed when I learned this result because this is a hard thing and this is a hard thing, and something nice happens to this hard thing if you do some averaging. In particular, you get some simple answers if you average over these things. And the fact that there's this one-to-one correspondence means that the holographic duality doesn't do that averaging for you, like it does the thermal averaging. So I was a little disappointed by this, but I think nevertheless it's an exciting thing, and so you should listen to Shiraz. Okay, but this is a good place to stop, maybe.
Questions on how to compute any correlation function that you like in ADS-CFT?
Can you come back to alternative quantization now?
Ah, yes, good. Okay, I knew that slide wouldn't get skipped in the end. Okay, so the thing I wanted to say about it, so now that I explained the Gibbons Hawking term, it's easy, is just that in a certain window of masses, that both of these are real. It's possible to construct another CFT from the same bulk theory. And the reason that Klebanov and Witten knew that they should be looking for this was that the lowest dimension, the lowest value of delta plus that you can get from this formula is d over 2, is that right? M squared is minus that. Yep, it's d over 2, where this is 0, that's this value. But we know that it's consistent with unitarity in the field theory to have dimensions as low as d minus 2 over 2. That's the dimension of a free scalar field in d dimensions. And so this encouraged these smart people to look for another way to construct a field theory from the same bulk. And if we consider variations of the field with finite, which produce a finite change in the action, then we could imagine a situation where those variations are dynamical degrees of freedom. And with the action that I used before, this variation in the action is only finite if d is bigger than d over 2, if delta is bigger than d over 2. But if we add a certain boundary term, which is of this extrinsic form, it depends on radial derivatives of the metric, we could actually cancel off the leading divergence here and make it so that fluctuations with z to the delta, that go like z to the delta, can be, profiles of phi that go like z to the delta can be finite action for smaller delta. And but the end result of this is just that if you instead treat the thing which previously was the subleading term as the source, and the other one which previously was the source as the response, then you get a different theory where the Green's functions are just flipped over. It's it's the ratio of the things in the other order. There's a nice interpretation of the relationship between these two theories, which is that the alternate quantization theory has an extra relevant operator, which is just O squared. So in the window where you can do this, O squared is always a relevant operator because the dimensions of operators in this large N theory add, and the dimension of O is, where did we go? It's delta minus is d over 2 minus this thing, which you can check with the conditions I said is twice it is always less than d. And so perturbation by this operator leads back to the ordinary quantization. Okay, that's the story of the alternate quantization.
Okay. Since you mentioned it, why is the quantity eta over s significant? Like, why are we dividing eta by s? Like, I mean, just because it's dimensionless?
Yes.
But there's no physical content in dividing by s, or
is there physical content in divided by s? Well, this quantity is yeah, that's not fair. I mentioned it very briefly. It's okay. In a limit, in a non-relativistic limit, if this is a natural quantity to consider because it's no, okay. Let me just say it's dimensionless. That's the answer.
Can I
Yeah,
answer?
yeah. Please, you should answer.
There is a certain physical, even if you consider certain modes, like propagation of sound, for example, or things which you actually physically measure, like attenuation of sound. So eta over s enters the formulas, not just viscosity, but this ratio. So if you want to perform a physical experiment where you measure how far your sound propagates and so on, you actually measure eta over s rather than eta. So that might be a more physical application why you want to divide this.
In ADS-CFT, can one study the cosmological constant at the boundary?
Cosmological constant in the boundary. You mean the 0-point energy of the field theory? No. I guess I have to say more than that. Yeah, the field theory is not coupled to gravity, right? The field theory of the boundary is not coupled to gravity. So a priori, you can change the add constant to the Hamiltonian. Doesn't change anything. Now you may be able to be clever and do something more complicated than what I've talked about, like maybe studying finite size behavior. So put the field theory on some space of finite volume and study the dependence on the volume. Maybe you can learn something that way. Yeah, I guess if studying the extensive part of the energy in finite volume is a sensible thing, which is meaningful, which you can compute holographically. So yes, okay, I take it back. I was wrong. Yes. Yes.
But at least for the negative cosmological constant, isn't there something like a boundary doesn't have a boundary? So I mean, so if the boundary theory had a negative cosmological constant, then you could find a boundary of that, and then.
Well, no matter what, it's not gravitating, right?
Yeah.
Yeah, but, excuse me.
Yes.
If you play that game, then you would have to be very careful in how you define your boundary. For instance, if you put, let's say, you're saying, I want to study a Schwarzschild black hole on the boundary, because I can choose which representative I put on the boundary. Then you put a Schwarzschild black hole there. The problem is that the boundary of that spacetime is not going to be the Schwarzschild black hole you put, because there will be identifications that you have to do in order to define the boundary properly. And basically, you will fall back to your original statement, and your boundary will not be the Schwarzschild black hole.
Wait a minute. You can put the Schwarzschild black hole on the boundary. You can put whatever you want on the boundary. I mean, these solutions have been constructed.
You can
like
put
droplets,
whatever you
like
want,
funnels.
but the boundary of that spacetime will not be your Schwarzschild black hole.
Well, of course. I mean, on the boundary, you put the Schwarzschild black hole, right?
You have to be careful in how you define a boundary.
What do you mean by that? I mean,
You have to subtract all the poles in the metric.
Constructed.
You have to subtract all the poles in the metric. So if you put a Schwarzschild black hole on the boundary, define some sort of second radial coordinate, which also goes to 0.
You're free to specify whatever boundary metric
agree
you
with
want.
that.
It's an elliptic problem, right? I mean, you
I agree
specify
with that
your data, you
statement.
integrate in the middle, and you're done.
I agree with that. I'm just saying that if you do this, then what you think is the boundary is actually not the boundary.
Follow your statement.
Okay, we can.
There is an ambiguity by the conformal rescaling.
Apart up to a conformal factor,
Yeah.
you can do what I mean.
I'm completely agreeing with that statement. I'm just saying that if you put a Schwarzschild black hole on the boundary and you take z to 0, then you have a problem because your Schwarzschild black hole on the boundary, you could also take r to 0. Then you have to tell me how you go to the boundary.
Yes.
And if you do it properly, then you will find out that the boundary is still the same ADS boundary that you had in the beginning and not the Schwarzschild black hole.
There is a rather dubious de Sitter CFT proposal. You slice de Sitter in some way, de Sitter slicing, and the dual of de Sitter is a holographic theory on the de Sitter, but that's also a gravitational theory, so you can slice it again and until you get down to quantum mechanics.
Did you read that?
Yeah. Other questions? Please.
I have a question about quasi-normal modes.
Quasi-normal modes.
I think that for the reason of stability, the imaginary part of quasi-normal mode frequency should be all on the half plane.
Ah, yes. If the system is stable.
Yeah. Should we observe it for any black hole or asymptotic areas?
You're asking, you're asking whether the imaginary part of the frequencies of all the quasi-normal modes for any black hole in edge of de Sitter space is positive. The answer is no. There are some black holes that are unstable. For example, charged black holes in the presence of scalar fields of sufficiently small mass and large enough charge will exhibit a quasi-normal mode for the scalar field, which is in the wrong half plane. whichever one gives when you Fourier transform gives a growing behavior in time.
Depends on your definitions.
Yeah.
Okay, if there's no more questions, we have two things to do. One is to thank John again, but before and after that, there's wine. Thank you.